I'm back, and we're thinking about describing the universe today. And this is through measurement, and then by looking at that data and seeing what patterns show up in that data. So we're looking to measure things and give them a number measure. So this is a quote from Lord Kelvin: when you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot measure it in number, your knowledge may be of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thought advanced the state of science. So we're going to be putting numbers on things so that we can create scatter plots. And that helps us see the relationship between the two variables that we plot, one on the x, one on the y-axis. So first, let's just talk about measurement and the differences between measurements, calculations, and estimations. So a measurement uses a tool to take a measurement of something. How well that thing is measured is based on the tool that you use. So I can measure my height in hands, right? I can stack my hands on top of each other and figure out how many hands tall I am. But that's not very precise. So we would use a meter stick or a measuring tape or a 2-meter stick to measure my height. A calculation is math. So you've done the math. So you're typing something into a calculator, you're multiplying two numbers together. That isn't a measurement, that's a calculation. And then an estimation is an educated guess. I guess that you're about 5 feet tall. In this class, we're going to use the Standard International System of Units. That's meters, kilograms, and seconds, or MKS. So our standard unit of length is going to be the meter. 1 meter is 100 centimeters. That prefix centa is in your reference table, and it means 10 to the negative 2. And about 3.3 feet is 1 meter. Mass, we're going to use kilograms as our mass. And 1 kilogram is 1,000 grams, and it's about 2.2 pounds. In chemistry, you're probably used to working in centimeters and grams, so we just got to take that next step to meters and kilograms. And then in time, we'll use seconds. So for length, how do we measure length? So we can measure length with a meter stick. We can get down to the thousandths place on the meter stick. So the tenths place is 10 centimeters, the hundredths place is 1 whole centimeter, and we can get down to the millimeter on that meter stick. We could also just use a ruler. If it's a smaller thing, we might want to use a ruler, or we could pace it. We could do hands, or we could pace it with our legs, but to be nice and precise, we would use a meter stick or a ruler most of the time. For mass, we would use a scale. So that's a digital balance. That we have 2 digital balances that we'll use. So one goes up to 200 grams, and that's the max it can do. It has much more precision. It can go down to the nearest hundredth of a gram. And then the other scale is only 2,000 grams. A bathroom scale would go to the whole kilogram. For time, you would use a stopwatch, but that's pretty uncertain. If you start and stop a stopwatch as fast as you can, usually people can only do that in about 0.2 seconds. So there's a large, 0.2 seconds is pretty big in terms of things that might be falling for only 1 second. So to be more precise, there's something called a photogate timer that we'll get into, and it has a resolution down to the 10,000ths place for timing. So there's different ways to time. Stopwatch, you could look at a clock, or you could use what's called a photogate timer. The lab that you're doing focuses on patterns. So there are 4 patterns that we're going to see in AP Physics, and by patterns, I mean just mathematical relationships. So these are the only 4 we're going to see in physics, which is pretty amazing. So the first one is your direct relationship. That's a linear function. It is given by the equation y equals mx plus b, where the y is the data plotted on the y-axis, x is the data plotted on the x-axis, and then the slope is that coefficient before the x. So if we plotted circumference versus diameter, we should get as our slope pi, because we know, and we can look in our reference table, that the circumference of a circle is equal to pi times the diameter. And there would be no y-intercept in that case because a 0 diameter circle would have 0 circumference. So there's a 0, 0 y-intercept. So in this lab, that's what we're hoping to see, is hoping to see a slope, that number before the x in our line of best fit equation, that is close to 3.14159 for our slope. So the next relationship that we are going to see often, we'll see in this lab, is called a quadratic relationship or a direct squared relationship. So the direct squared just kind of leaves off the other terms of a quadratic and just focuses on the x squared term. So a direct squared relationship has some constant proportionality a, and then x squared in the equation, and we can see that it increases at an increasing rate, which generally can be described with the word exponential. But in mathematical relationships, there actually is an exponential function. It's called e to the x, or it's defined as y equals e to the x. So this is a different function. This is what we'll call direct squared or quadratic. And something we're going to do a lot in this class is linearization. So we can prove that area is directly related to radius squared by squaring the radius and plotting that, and with respect to the area, and seeing if it's a linear relationship. So that's something called linearization, where if it's not clearly linear, we can figure out what power, what dependence it might be, then try to plot our y versus x squared, and if it is linear at that point, then we know it's linear. If you did that with our e to the x function, it would not be linear. So that differentiates a direct squared function from an exponential function. The other two patterns we'll see are kind of the same. Inverse, so not the same pattern, but it's instead of y is directly related to x, it's y is directly related to 1 divided by x, or some constant a divided by x. And 1 divided by x is the same as x to the negative 1 power. So the inverse relationship that we can see is if you're trying to fit a bunch of text on a page, you can narrow the margins or open up the margins so it all fits on one page. Or if you haven't written enough, you can bring those margins in and it'll fill it up to one page. One of the features of this function is it can never be 0. So we can divide by bigger and bigger numbers, but y is never going to reach 0. So there's an asymptote at the y and the x-axis for an inverse relationship. And then the last one that we'll see in this whole course is an inverse squared relationship. So similarly to the inverse relationship, it's inverse squared. And we can plot y versus 1 over x and see a direct relationship to prove or linearize an inverse relationship, and we'll do more practice with that. So we're going to measure, we're going to plot data in Excel, and we're going to look for our relationships, and they are either direct, direct squared, inverse, or inverse squared.